Hi everyone, welcome back to part 4 of chapter 7. In this video we're going to go over how the variable force discussions that we had in the previous video are going to apply to a very common type of variable force known as springs. And once we get a definition for those spring forces, then we will apply that to how a spring can do work. And from there, we'll actually segue into the Chapter 8 material, which will take the idea of work and the change in energy, and we're going to basically mold that into the conservation of energy law. What that will do is basically if we can conserve the energy, or rather if we can keep track of all the different forms that the energy is in, then we don't have to actually do the math for the work, which is kind of nice, because our definition of work still requires us to play around with the vectors a little bit, in that we have to evaluate the work done by a given force, and then if of course if that force and displacement were given in component form, we could evaluate the work that way as well. But if we can keep track of the energy in all of its forms during the motion of the object, or during whatever actions that object is going through, then we don't actually have to do work in terms of the mathematics. We can just fill in the values for the different energies as we go. But we need to start at the beginning, obviously. So we're going to talk about spring forces, how they work, and ultimately what kind of work they're going to do. So we're going to draw ourselves a spring that is anchored to a wall. And, oops, there we go. So here I have a spring, and I've got it anchored to the wall on the left, and then I'm going to attach a small plate to the end of the spring. And this plate is there so that the spring can interact with a mass. So in other words, we might have a mass put here that our spring can interact with at a later time. Right now we just want to focus on the spring itself. And we're going to set up the spring. It might wobble a little bit until it comes to a rest. And that point where the spring comes to rest is going to be important to us, because this is going to be called the equilibrium position. Oops, I think I spelled that wrong. Okay, there we go. And we're going to label that 0. And any displacement from that equilibrium position will be measured just like we would on a number line. And so we would have 1, 2, 3, 4 going off in the positive x direction, -1, -2, -3, and so on. And we'll say that this is in centimeters. As a spring is displaced from its equilibrium position, there's a reason why the spring is at equilibrium, and that's because there is a net force of 0 at that location. And a spring is very much like a college student. If you try to remove that spring from its rest position, so if I were to try and apply a force to, drag you out of bed or something in the morning, then you are going to resist by pulling back. and wanting to return to rest. And this doesn't matter if the applied force is stretching the spring out or if the applied force is compressing the spring. In either case, the spring force wants to return back to equilibrium. And this will be our first concept for the spring, is that spring force always points towards the equilibrium position. And this is going to be very important when it comes to figuring out what kind of work the spring is capable of doing. Now, we'll focus our attentions just on one of the two displacements. We'll stretch the spring out, and then we'll talk about any differences that there might be with compressing the spring. But what we're going to do next is we're going to graph the situation. We will graph the applied force versus the spring force. So we'll start at 0. In other words, we have 0 applied force, and that means that the spring is going to be sitting at its equilibrium position. And if the spring is at its equilibrium position, it doesn't require any restoring force. It doesn't require any value to bring it back to equilibrium. But then we're going to start increasing that applied force. We will slowly increase this applied force. And as we do so, what we find is that as we displace the spring further and further away from its equilibrium position, the spring force actually starts pulling back with a greater and greater magnitude. This means that we have to apply a greater and greater value of applied force if we want to continue displacing the spring from equilibrium. And this means that we see a one-to-one relationship between the spring force and the applied force. So we'll apply some applied force, and the spring will end up displacing a certain distance under the influence of that applied force, but then the spring will ultimately stop at that new displacement because the spring force will be providing an equal and opposite magnitude. Well, we can take this idea of a changing spring force, because right now we just have the one-to-one relationship between the two forces. So whatever the applied force is, that's the magnitude of the spring force. But I would rather get an expression for the spring force in terms of the displacement. If our spring force is going to change its magnitude as we stretch the spring out, in other words, the magnitude of the spring force is going to become greater and greater the further we displace from equilibrium. So the greater the value of x, the greater the value of the magnitude of our spring force. But this isn't the entire equation. If we were to graph a spring in general, just any spring, with respect to changing displacement, well, some springs are kind of flimsy, like a slinky, and you can actually displace those springs a pretty fair distance without encountering much of a spring force in response. But then you have some springs that are very, very rigid, like the springs that you have on your car in the suspension. And in those cases, you run into a very, very steep graph where you just displace the spring a tiny bit and you run into this tremendous amount of force. And then we have forces that are everywhere in between. And so all these different lines, all these different slopes are measurements of essentially how stiff or rigid the spring is. And we call this ratio the spring constant. And we give this the name of little k. And it is important that we don't get this mixed up with capital K, which is our kinetic energy expression. So I'm going to make sure that we see this as a little k here. Give it a very large cap there. But the spring constant is effectively measuring how stiff the spring is. And so the greater the spring constant, the more force that will result as we displace the spring. And that means that we can put together an equation for our spring. Our spring force will have a magnitude that is equal to K times the displacement from equilibrium. Different springs will have different spring constants. Again, the larger the spring constant, the larger the amount of spring force that we will see. Now, this equation is almost complete. There's one thing that we're missing. If we look up here where we are stretching the spring out, actually I'll go ahead and redraw it down here. So we have our spring at equilibrium, and we're going to stretch the spring out to some new displacement that we'll call D, and I'll draw that displacement in a different color. So we've displaced our spring some amount of positive D, or actually let's just call it X. We'll just call it positive X. We're going to come out here to positive X. There we go. But as we remove the spring from equilibrium, the spring is going to provide that counterforce that points in the opposite direction. Well, this equation does not yet reflect that idea. And remember that a spring force is still a force, and a force is a vector. A vector has to have a direction. Well, it does. We can see it right here. But that spring force is pointing in a direction that is opposite of the displacement vector that we are using. And that equality between the two says that not only do we have to have the same numbers on both sides of the equation, but we have to have the same directions as well. And that's not what we're seeing. If we compare this to a case where the spring is being compressed. So let's take our spring at equilibrium, and we will compress it back to a point of negative X. So that requires a displacement in the negative direction. But the spring force is going to point back towards equilibrium. The spring force always wants to point towards the equilibrium position. And again, we run into a situation where the spring force is pointing in a direction that is opposite of the displacement. So how do we fix that? Well, we'll just incorporate a minus sign into the equation. And we now have an expression that defines the spring force. And this is called Hooke's law. So as we displace a spring away from its equilibrium position, the spring will respond with a counter force, hence the negative sign. And now that we can see what the spring force is, our next goal is to figure out how much work is involved as that spring is displacing, because we have a spring force, and we know that by definition, work done by a force is the dot product of that force and the displacement vector. Okay. So we will once again go with the stretching scenario. We want to displace our spring from equilibrium out to some positive x value. As we do that, the spring force will counter by pointing in the opposite direction. Now, our displacement vector is pointing to the right. Our spring force is pointing to the left. If we plug this into our dot product relationship, well, magnitudes aside, the angle relationship between these two vectors, as we move the spring away from equilibrium, is 180 degrees. Displacement is pointing to the right, force is pointing to the left. And that's going to result in a -1. And so does that just mean that we have negative times the value of the magnitudes? Well, what's the magnitude of the spring force? Well, the spring force is constantly changing as we displace. And so I can't actually say that the spring force has a magnitude, and that means that I can't use this approach. Now, this part is still valid. We're still going to end up having negative work done, but we need a different way of describing how this force is doing work. And that's what the previous video allowed us to do. If we have a force that varies with respect to position, which is exactly what our spring force is doing, we can integrate that force about the limits of our displacement, and we can find out how much work is done. So we are looking for the work done by the spring, which is going to equal the integral of the spring force as we go from some initial to final position. In our case, we're starting at the equilibrium position, and we're going out to a final position of positive x. We will enter the expression for the spring force, which is negative kx. And we're going from 0 to positive x for our limits. K is a constant, spring constant. Just to be consistent here, the spring constant will have units of newtons per meter. But in a lot of our example problems, you're probably not going to find a whole lot of springs that will extend or compress by meters at a time, which is why you're more commonly going to find a spring constant labeled in newtons per centimeter. But that means that you're going to have to convert it to newtons per meter before we enter that into any of our expressions. All right, so K is a constant that can be brought out front along with the minus sign. So we have a minus K, and then the integral of x with respect to itself, that becomes x squared over 2. So we have minus K x squared over 2 evaluated at our limits. When we plug in x, we get x squared, but we still have the minus 1/2 k out front. And then we have to subtract the same evaluation at 0, but that's just going to make 0. And so there's the work done by the spring as we go from the equilibrium position out to positive x. Now, it is worth noting that we don't necessarily have to have our spring starting at 0. These integrals are set up to go between any 2 points along that number line. So if we upgrade this integral to a more general case, we have negative 1/2 k x squared. That's what we got out of the evaluation of our integral. And then, well, we can have any set of initial and final starting points that we want. We just have to evaluate at those specific values. So we've got negative 1/2 k. I'm going to factor that out because both terms will have a minus 1/2 k as part of the evaluation. But we have x squared evaluated at x final, and then we have to subtract x squared evaluated at x initial. Okay, we are subtracting the evaluation. Okay, we are not taking negative x naught and then squaring it. This minus sign is out front. And so there's the work done by our spring force between any 2 values on the number line. Now we still have this minus sign out front, and that would almost imply that the spring force always does negative work, but that's not actually true. Whether or not this spring force comes out to be a negative number really depends on what this difference is. Remember, we can start between any 2 points on the number line that we want. And if x initial squared ends up being a larger quantity than x final squared, then we could get a positive work out of that expression. So let's see how this might be possible, and we'll put in some values for an example problem. We'll say that we have a spring constant of 20 newtons per centimeter, and we're going to take the spring from equilibrium and we'll stretch it out to a position of x equals 10 centimeters. And I want to know how much work the spring does during that displacement. Well, our equation, our general expression, is right there. The only thing that we need to do is convert our spring constant to centimeters, and we need to convert our position from centimeters. Now, you might be looking at this and saying, well, they're both in centimeters. Won't they combine accordingly? And The answer is no, and that's because your spring constant depends on centimeters, but you're going to end up with centimeters squared in the brackets, and that's not going to give us the proper units for work. So it's best if we just convert everything to meters right away. So we get 100 centimeters for every meter. That means that we have 2,000 newtons per meter for the spring constant. And our final value for our x position, 10 centimeters, is going to be 0.1 meters. Here we go. Spring force is minus 1/2 spring constant, 2,000. The final position squared, 0.1 squared, minus the initial position squared, 0 squared. So what are we going to get? Well, given the way that everything is laid out in the math here, we're going to be getting a negative number. But that was to be expected because we are displacing ourselves away from equilibrium. And as we do that, the spring force is going to be pointing back. Alright, so I'm getting my calculator app to open here. It's being slow for some reason. But we have half of 2,000, which is 1,000, times 0.1 squared. And that's going to come out to equal 10. Negative 10. And joules. There we go. All right, so work was done by the spring in an amount of negative 10 joules, getting from the equilibrium position out to the 10 centimeter mark. So let's allow the spring to return to equilibrium. So if we do that, the displacement of the spring is now going to be back towards the equilibrium position. The spring force always points towards equilibrium, and now we can see that the spring force and the displacement vector are pointing in the same direction, and that means that the angle relationship is 0. Cosine of 0 is positive 1. We should expect to see work done that is positive when we return to equilibrium. In other words, the spring force is helping us to return. Whenever a force helps us to move in the direction of the displacement, that's positive work. When we removed the spring from equilibrium, we were traveling in a direction that was opposite of what the spring force was pointing, and so the spring force was working against us, hence the negative sign. Okay, let's take our spring force and the work that it does. So the work done by the spring is 1/2 k x final squared minus x initial squared. And we'll evaluate this for the return trip. Now, the important thing about this is that our initial and final position values have swapped. We are now starting at the 10 centimeter mark, and we are ending at equilibrium. So we need to switch those values around. And if we do that in the brackets, all that happens is that the two terms switch places, and that causes the sign on their outcome to become negative. So we now have a negative 1/2 times 2,000 times a negative 0.01 squared. So 0.01 is going to become 0.1 squared becomes 0.01. But there's a minus sign waiting outside to turn that squared compound into a negative. That negative is going to cancel with the negative out front, and, well, numerically everything is just going to come out to equal the same 10 joules, only it's positive. So we did negative work moving the spring away from equilibrium, but we did an equal and opposite amount of work returning the spring to equilibrium. In other words, we just went on a closed path journey. We went out to 10 centimeters, came back, and the net work that was done by the spring during that closed path journey was 0. And this means that a spring force falls under the definition of a conservative force. A conservative force is a force that conserves the amount of work that is done over a closed path. Well, how is this going to be any different if we allow the spring to compress instead of stretch? And I think you'll see pretty quick that there's actually no difference. Let's take our spring. We will displace it back to negative 10 centimeters. As we do that, we are removing the spring from equilibrium. The spring force is going to point back towards equilibrium. Those two vectors are pointing in opposite directions. We should expect a negative amount of work to be done by this spring. We'll put the values into our equation. I'm going to go ahead and just keep all the same values as before. So we have the same spring constant. The final position is at negative 10 centimeters, so that is negative 0.1. That value has to be squared. We have negative 0.1 squared minus the initial starting point was 0. Well, in this case, we're actually squaring the negative term, and we get positive 0.01 minus 0 times half of 2,000, and well, we're getting a negative 10 joules. So whether we've displaced 10 centimeters in the positive direction or 10 centimeters in the negative direction, in either case, we have displaced our spring away from the equilibrium position, and the spring has done negative work in equal amounts. So it doesn't matter if we're stretching the spring or compressing the spring. All that matters is that we are removing the spring from the equilibrium position, and we're going to do the same amount of work over the same displacement either way. Well, if the spring is in fact a conservative force, then we should do an equal and opposite amount of work if we allow the spring to return to equilibrium. Let's find out. Our work expression says half of spring constant, and I'll just put the numbers in. You know what the equation is. But we're traveling back to equilibrium now, so that means the initial and final values need to swap places. Our final position is now 0. Our initial position is the negative 10 centimeters. Now we've got to be careful with our algebra here, because back here when we evaluate this, how many negative signs do we have? Well, there's 1, 2, 3 negative signs. We have to start by squaring the value of our position, and that's going to result in a positive 0.01, but then there's a negative waiting out front. And then, well, there's another negative. So in total, there's 4 negatives. And even numbers of negatives is going to result in a positive. So half of 2,000 is 1,000, and this is going to result in a positive 10. Exactly what we were expecting for a conservative force. Now, again, keep in mind that you don't have to always start or end at the equilibrium position. We could just as easily ask how much work is done getting the spring to go from negative 10 centimeters out to positive 10 centimeters. Well, we've already seen that when a spring returns to equilibrium, it does positive work. But the moment we pass that equilibrium point, once we pass that equilibrium position, the spring is going to start doing negative work. So how much total work do you think the spring is going to do, getting from the 10 centimeter mark out to, the negative 10 centimeter mark out to the positive 10 centimeter mark? Well, we could do this a piece at a time. We could go from negative 10 to 0 and then from 0 to 10. Or we could just let the equation do its job. We want to start at the initial position of negative 10, and we want to end at the final position of positive 10. So final position, positive 10, 0.01 squared. We have to subtract the squared value of the initial position, which is negative 0.1 squared. Getting too close to the edge of the screen there. And again, we have to be careful with how we evaluate everything. But 0.1 squared is 0.01. We have to subtract the square of negative 0.01, which we square a negative, it becomes positive. Well, what's happening here? We have 0.01 minus 0.01, which is 0. So the spring has done a net amount of work equal to 0, getting from negative 10 out to positive 10. That should not be a surprise, because we already know that as the spring returned to equilibrium, we've done this. We went from negative 10 to 0, and we got 10 joules of work. We also know what happened when the spring went from our equilibrium position out to positive 10. There was negative 10 joules worth of work done, and combined, that is 0. Well, does this repeat the definition of conservative force? In that case, no. This is not actually telling us that the spring is conservative. If you'll remember, the definition of a conservative force says that you have to do a network of 0 over a closed path. We are not operating under a closed path. We started at negative 10. we ended at positive 10. Even though the network was 0, we don't have a closed path here. To accomplish that, we would have to let the spring go back to its original starting point. But you know what? We've already done all of that work as well. If we let the spring return to equilibrium, we'll do positive 10 joules of work. But then the moment we pass equilibrium and go back to that negative 10 centimeter mark, we're going to do negative 10 joules worth of work. So let's see here. During the entire closed path, what do we have? We have 10 minus 10 plus 10 minus 10. Well, that's all giving us a net work of 0 over a closed path. So yes, we've once again confirmed that a spring is a conservative force. All right, so we have our spring force defined. And we also have our spring constant defined. And the minus sign is there to remind us that anytime we displace our spring, the spring force is going to point in the opposite direction. We've used that spring force to evaluate and tell us what the work done by the spring is going to be. And since we've already gone through and we've done the integration, we don't have to reproduce this. This outcome is true for any spring. This is a general expression for how any spring is going to operate. The only thing that makes one spring different from another is the spring constant, and that's measuring the stiffness or how rigid that spring is going to be. And now that we know how much work a spring can do, if the spring is the only force that is operating in the system, then the spring force automatically becomes the net force, or the work done by the spring automatically becomes the net work. And that means that the work done by the spring is responsible for whatever change in kinetic energy that we see in the system. Now, I'm going to stop the video here just because this is a good place to stop. But I'm going to do a fifth video for this chapter that just involves a couple of example problems. So if you want to watch that video, you can. It's not going to include any additional content from the chapter. It's just going to show the application of some of these ideas. And then after that video, we'll progress on to the Chapter 8 material. So we'll see you in Chapter 8.